Hello and welcome to today's video. Today's video is for Advanced Geometry Chapter 12, Section 3, Inscribed Angles. So we're going to have some theorems for this section dealing with inscribed angles, and first we start out with a couple definitions. So first we have intercepted arc. An intercepted arc is an arc contained within an inscribed angle. So if you take a look at this picture here, first thing I have is an inscribed angle. An inscribed angle is an angle whose vertex is on the circle, so notice C is on the circle, and whose sides intersect the circle. So it intersects at B and A, so this is called an inscribed angle. Now, an inscribed angle always intercepts an arc, and that arc goes between the two places that the angle intersects the circle. So this is called an intercepted arc. So first thing we have is an inscribed angle theorem. This one says that the measure of an inscribed angle is half of the measure of its intercepted arc. So we learned before that if you go from a central angle, so if I add another point in here, I call it the center of the circle, and I'll call him D. And I'll call this 1, and I'll call this 2. So we already know that the measure of angle 1 is the same as the measure of the arc. So the measure of angle 1 equals the measure of arc AC. And now we also know that the measure of angle 2 is 1/2 of the measure of arc AC. And then if we wanted to, we could also say that the measure of angle 2 was half the measure of angle 1. In order to prove this theorem, we actually have to have 3 proofs, because there's 3 different versions of this. One in which the center of the circle is on one of the sides of the angle, one in which the center of the circle is inside the angle, and one in which the center of the circle is outside the angle. Okay? And we're going to prove one of these in class. So we're going to prove the one where the center is actually on the circle, or sorry, the center of the circle is on the side of the angle. And you guys are going to do a couple of the other ones for homework. So there actually has this kind of cool, because to prove this theorem we actually have to prove all 3 cases a little different. Now this one has corollaries. There are 3 corollaries. The first one says that 2 inscribed angles that intercept the same arc are congruent. So if I draw a circle, and then I'm actually going to draw the intercepted arc first. So suppose I have this intercepted arc, and I'll call this A and this B. And if I draw 2 angles that go from A to a point on the circle and then back to B, so maybe this one here and this one here, then these 2 angles have to be the same measure. So measure of angle 1 would be the same as measure of angle 2, because they intercept the same arc. They're each 1/2 of AB, so they each have to be congruent to each other. So there's the first corollary. The second one says that an angle inscribed in a semicircle is right. So for this one, if I draw a circle, and then I draw a diameter, and then I draw any inscribed angle in this diameter, so it can go anywhere, then that angle is going to be right. And it doesn't matter, I can draw it really just to the side here and then go all the way across, and this is still a right angle. The reason why this one works is because the measure of the inscribed angle is half of the arc. Well, the arc is 180 degrees because it's a diameter, so half of 180 degrees, 90 degrees. And the last one I have is opposite angles of a quadrilateral inscribed in a circle are supplementary. So if I draw a circle, and then I put 4 points on here, anywhere I want them, and then I connect it to make a quadrilateral, what's always true is the angles across from each other are going to be supplementary. And the reason for this one is because if you take a look at inscribed angle number 1, well, he inscribes, let me get a different pen, he inscribes from here all the way around here, and if I take a look at the other one, angle 2, he inscribes the rest of it. He inscribes from here to here. So if I put those together, I get 360 degrees all the way around the circle, So if I take half of that, I get 180. So if I add 1 and 2 together, I must get 180. Okay, so a couple examples. Let me find the measure of each of these angles. So if you take a look at the first one, this one's inscribed in a diameter, so measure of angle 1 equals 90. It didn't even matter what the other ones were. And for this one, well, this is inscribing the same arc as angle 2. So the measure of angle 2 must also be 38 degrees. And if you wanted to, you could go to the arc, so it would have to be double it, so it would have to be 76, and then you could take half of it again if you wanted to. Okay. The last one we have is the tangent chord theorem. This one says the measure of an angle formed by a tangent and a chord is half the measure of its intercepted arc. So it's kind of like the inscribed angle, except for this time we've got one chord, but then you also have a tangent. So tangent chord theorem. Put a circle in front of it. So the easiest way of proving this one is actually to start with an inscribed angle. And then what you can do is, we know that as long as the angle goes through B and C and inscribes BC, then angle A isn't going to change measure. So what we can do is we can see it rotating around. Well, it's still inscribing BC, so the angle hasn't changed. And here it's getting closer to C. Angle hasn't changed because it's still inscribing BC. And then finally what happens is we coincide A to C, and it's still inscribing the same angle, so that angle is still going to be the same. So it's not a proof, but it's a nice way to think about it. You just rotate A from an inscribed angle till it meets up with one of the other intersection points, and you end up getting the chord tangent theorem. Okay. And that's it for today's notes. Thank you for watching. Have a great day.